Good morning, everyone. I want to believe that everyone can hear me. Okay. So we are looking at the beginning part of our chapter 15, which is traveling waves and sound. We'll be looking at this and other subheadings to buttress the points about traveling waves and sound. All right. We'll have this image before us, the image of a bat, which is a typical example of how that animals make use of waves and signals to better survive in their habitations. Okay. So the bat is one of the animals that we know that makes use of sound waves to locate prey and also to navigate in the air. We'll be looking at that and the application of sound waves and other forms of wave in this topic. Okay, so as usual, we'll be having three major blocks of discussion, one of which is the traveling wave, and we'll be emphasizing how that we use the wave model to describe phenomena of the moving wave. We'll also want to describe waves as sinusoidal and other forms of waves. We'll look at the wave equation as well. We'll also finally look at the ending part, which is the energy and intensity. All right, so we'll be looking at energy and intensity as it relates to waves that are concentrated to a location and those that are spreading out. Okay, so we'll begin our discourse by looking at the wave model. So the wave model, like we've seen before in our previous class when we looked at the particle model, we use the particle model to describe the object or a whole system as a dot. But when it comes to wave, and we're talking about wave model, wave is a more complex system in the sense that we cannot just summarize the whole system as a dot like we did in the case of particle model. But when we talk about wave model, we're actually talking about the model in the aspect that relates to all wave. Okay, so the wave model is built around the idea of traveling wave, which is an organized disturbance that travels with a well-defined wave speed. So because it's the disturbance that happens in the whole system, we just cannot use a dot to represent it. So when we talk about model, we're talking about the wave model with respect to traveling waves and how they relate or what they have in common with other waves type. All right, so the definition seems straightforward, but we must understand several new terms to gain a complete understanding or holistic view of the concept of traveling wave. So we'll be using the model, which is the similarity or common grounds for all wave to understand these concepts. So when we talk about wave, we talk about wave under two broad headings, which is the mechanical waves and the electromagnetic, and the third one, which is matter waves. We will not dwell so much on matter waves, so we'll be emphasizing more on mechanical waves and further into electromagnetic wave as well. So what do we mean by mechanical waves? Mechanical waves are waves that involve the motion of substance through which they move sorry, one moment, okay. So mechanical waves are waves that involve the motion of substance through which they move, that is the medium. For example, the medium of the water wave is the water, and the medium of the sound wave is the air. The medium of a wave on a stretched string is a string, okay? So we're looking at mechanical wave, that is wave that travels through a medium, or they require material medium for propagation. So as the wave passes through a medium, the atoms that makes up the medium are displaced from equilibrium. We've seen before when we described when we were describing wave, and when we were describing simple harmonic motion, we talked about displacement from equilibrium position. So when we use the word equilibrium position, you understand what we mean. So as the wave travels through the medium, what actually happens to the atom of the medium is that they are displaced from equilibrium, and they give us what we call the ripples, or the trough and the crest. All right. So the displaced wave behave more like the spring that we've already seen or discussed in simple harmonic motion. So when a wave is disturbed or displaced from equilibrium, we say this is the disturbance of the medium. And the disturbance of the medium are usually created from the source. Example is what we have seen here in the figure. You see a source is being dropped here, and then the stable medium is disturbed, and the atom of that medium displaced from equilibrium. You see what we call the ripples, which is this distinct line, or better put in this form. Okay. Okay. So that's all about mechanical wave. So move on to electromagnetic and matter wave. We have said that mechanical waves requires a material medium for propagation, but it's not all kind of waves that require material medium. And one of such waves that does not require material medium for propagation is the electromagnetic waves, okay? So we have two important types of waves which do not require material medium for propagation, and they are electromagnetic waves and matter waves, all right? So electromagnetic waves are waves of an electromagnetic field. Electromagnetic waves are very diverse, including the visible light, the radio wave, the microwave, and the X-ray. When we talk about electromagnetic wave, the first thing that should come to your mind is that it requires no material medium for propagation, and it can travel through a vacuum. And they travel at the speed of light, okay? So light can travel through empty space, so also all electromagnetic waves. And one of the significant thing about the electromagnetic waves, the significant thing about matter waves is that they are waves whose material particles are the electrons and atoms. And we call those kind of waves that behave, particles that behave, that has the wave properties are described with the matter waves, okay? So we will learn the description of the full application of matter waves when we get to the last chapter of the test, not the last chapter for the semester, which is chapter 28. We'll dwell so much on what matter waves is. But for now, all we need to know is that they are material particles, such as electrons and atoms, that have the wave-like characteristics. So we refer to the class of particles as matter waves. All right, so we'll move on to the two types of wave motion that we have. We have two major types of wave motion. The first is the transverse wave, and the second is the longitudinal wave. The transverse wave describes the particle in which the medium moves perpendicular to the direction of the wave. Look at the medium. It's moving up and down, while the direction of the wave is to the right, as depicted by this arrow. So the medium is moving up and down, and it's perpendicular to the motion of the wave. That kind of motion is called the transverse wave. While for the longitudinal wave, the particle in the medium moves parallel to the direction of the wave. So the movement of the particle is this way, and the movement of the wave is also in parallel direction. So we'll have, if you have to pull and push a string, you will see areas that are compressed and the areas that are spaced out. We'll call the compressed area, and then we'll have the spaced out areas, which shows us that the particles of that spring is moving in the same direction as that of the wave motion, and these directions are parallel to each other. So we also have, those are the two major wave motions that we have, longitudinal and transverse. We want to describe how that the earthquake waves can actually take these two kinds of motion. We have already established that wave is the disturbance that is traveling, some through the medium or some through the vacuum. Okay, so we have the passage of the longitudinal, which is depicted by the parallel wave. On the system as shown in this figure, we have the parallel wave traveling internally on the ground. You see that the travel motion still keeps, there's a vibration going on, but the objects on the surface of the earth still remain in place. So, but when the earthquake motion is taking the S wave, which is the transverse, wave, you see the waving motion of the transverse. So the objects, they are not stable. The longitudinal wave is faster, but the transverse wave is more destructive when it comes to earthquake. So the earthquake that moves or occurs with the transverse wave is the one that causes more destruction because of the wave shape, while that of the longitudinal travels fast. The vibration happens, but it's less destructive compared to the transverse. So the earthquake, which is a kind of wave, can actually take the transverse or the longitudinal wave motion. So that brings us to the subject traveling waves. When we say traveling waves, we're actually referring to a wave that can carry energy from point A to B. They are not stationary, they are in motion. So how does a mechanical wave travel through a medium? We have established that traveling wave is the movement of a wave from point A carrying energy to point B. So we can use Newton's law to examine how the medium responds to the disturbance. Talking about medium, we're referring to the material medium through which a mechanical wave is transported. All right, so let's see how that happens, let's view this figure. The dot on this rope is what we use to understand the motion of the wave. So as the wave reaches this point with the dot, the curvature of the string leads to the net force that pulls the string upward. This is the force diagram of what is happening here. The wave at this dot has a net force that pushes it up. The tension on the rope, the tension in the direction of the wave, then there's a net force that pushes it up for the wave motion to travel across that point. Now, once the wave gets to its peak here, in the B section of the diagram, you see another net force pulling it down. That's causing the dots to come down. So at the peak, as the peak has passed the dots, the curvature of the string leads to a net force that pulls it down to be flat again. So a transverse wave pulse traveling to the right along the stretch string of these dots has the force, net force pulling it up, and the net force pulling it down. That is exactly how these forces controls the material medium to bring about the motion of that wave. And that is how the medium responds to the disturbance caused by the wave. Okay. So having established that the traveling wave is the wave that is motion, moving energy from point A to B, we want to move quickly to talking about sound wave. A sound wave, as seen from the wave that comes from our loudspeaker, is such that when a sound is produced with a loudspeaker, the electrical pulse pushes sharply on the air around the sound, which creates the compression of the molecules. And as the compression moves, waves are transported through the compression of air. We have the molecules of air, the compression, and the motion of the wave with the velocity of that sound. So this compression is the disturbance, and that is what travels through the air to produce the sound that we hear. Okay, so sound wave actually moves through the material medium called air to get to us. So we usually think of sound wave as traveling in air, but sound can actually travel in gas and through liquids, and also in solid, not just in air. Okay, so we want to look at wave speed as the property to propagate wave in the medium. So the property that we use to determine the wave speed when traveling through the medium is actually what we refer to as the linear density with the symbol mu. So the speed depends on the mass to the length ratio. And we call the speed dependence on mass and length ratio the linear density. So linear density is given by mu equal to m over L, m being the mass and L the length ratio to the mass. So linear density characterizes the type of string we are using. So the linear density is actually dependent on the mass, the length of string, and the type of string itself. So a fat string has a larger value of linear density than a skinny, thin string made of the same material. So the kind of string actually is what determines the linear density of the medium. All right, and another thing we should note about the string is that a string with a greater tension responds more rapidly. So the wave will move at a higher speed in a string with greater tension than one with less tension. A string with greater linear density has more inertia, so it is more resistant to change in motion or more resistant to displacement of its particle. Okay, so the lower the linear density, wave speed decreases with increase in linear density. If the linear density is high, the speed is low. If the linear density is low, the speed will be high. So the full analysis of the wave of the motion of a string leads to the expression that we'll have here to depict the speed of wave. All right. So the speed, wave speed on a stretched string with tension T and linear density is given by V string, which is the speed of the string, equal to the square root of the tension of the string and the linear density mu. Okay. So let's take an example to apply this formula. All spiders are very sensitive to vibrations. An orb spider will sit at the center of its large circular web and monitor radar thread for vibration created when an insect lands. Assume that these threads are made of silk with a linear density of 1.0 times 10 raised to power minus 5 kilogram per meters under the tension of 0.4 Newton, both typical numbers. If an insect lands in the web 30 cm from the spider, how long will it take from the spider to find out? Okay, how long will it take from the this M is there for the spider to find out? So we want to know the time it will take for the spider to find out that an insect just landed 30 cm away from its center of the web. So to solve this, first we determine the speed of the wave. So we determine the speed by using the formula that we just saw. The speed is given by the tension and the linear density. To substitute that directly into the equation as given, we have 0.4 Newton over the linear density to give us 200 meters per second. Remember, what you're looking for is how long, which is time. So the time for the wave to travel through the distance for 30 cm, since we have the speed, we use from the formula speed, distance with time. We can make this the subject of formula to get what we have here. So converting the distance to meters, we have 0.3 meters over the speed we just calculated to give us 1.5 milliseconds. So it takes 1.5 milliseconds for the spider to realize that an insect just dropped 30 cm away from its center. So you want to look at the property of gas that determine the speed of sound wave traveling through the gas. All right, so the thorough analysis finds that the sound speed is slightly less than the root mean square speed, but has the same dependence on temperature and molar mass. And it is given as the speed, root mean square speed being equal to 3 kbtm, where this is the Boltzmann constant, tension, temperature, and molar mass. Okay, we said it's dependent on temperature and molar mass. So if we have established that the sound speed is slightly less than the root mean square, and this is the root mean square speed, then we'll have the sound speed for sound traveling. Remember, we're talking about sound traveling through gas, to be given as the gamma kt over m. All right. Remember, we said a little less. So we have the same parameters here, repeated here, but there's a gamma sign. All right. So this is the sound speed in gas as it depends on temperature. We have the Boltzmann constant, time, temperature, and molar mass. So we have established speed. Remember this value? Okay, the established speed of the several speed of medium and their established value. I'm circling this one because we use this constant a lot, which is the speed of air when it is 20 degrees Celsius. Okay, so we'll have the big R there to mean the gas constant, the M for the molar mass, and the gamma, which is the constant that depends on gas, and it varies for different gases, for helium, for oxygen, and so on. So if you're given a question to find that, the constant will be given to you for the particular gas you're looking for or that is specified in the question. So let's see another example. On a typical Martin morning, the very thin atmosphere, which is almost entirely carbon dioxide, is a 40 to 100 degrees Celsius. What is the speed of the sound on such a morning? At what approximate temperature would the speed be doubled? The value. When would that speed be doubled its value at that temperature? All right, so the first question is to find the speed of sound. So we use the equation given to find the speed of sound and the value for carbon dioxide, which is 1.3, as seen in this particular constant here. So we substitute the gas constant, which is also an established constant, and the temperature also in Kelvin. Then the molar mass for carbon dioxide as well in gram per mole. All right. So we use that to calculate, substituting all the parameters as given. We took the square root and we got 210 as 210 meter per second at the speed of sound. So the speed of sound, remember, we're asked to find the temperature the approximate temperature that will bring the value that will double that value. So from the formula, we can see that the speed is proportional to the square root of temperature, right? The rest are constant typically. So to double the speed, an increase in temperature is required by a factor of 4 for this to double, because this is already the square root. to double it will give you a factor of 4. So doubling by a factor of 4 will have about 690 Kelvin or 420 degrees Celsius. Simply by looking at the formula and the square root relationship with temperature, we're able to specify that we need the factor of 4 to double that temperature as required. Okay. So we'll look at another example during a thunderstorm. You see a flash from lightning strike. 8 seconds later, you hear the crack of the thunder. How far away did the lightning strike? Okay, so one moment. Right. So we're asked to calculate how far away did the lightning strike? The time for light to travel 1 mile is given as in meters, the distance of 1 mile, which is 1610 meters. So the time, since you know the distance and the speed, we use the speed of light, which is a constant. So the distance in meters over the speed of light will give us the idea of the time. And this is actually 5 microseconds, right? So since we know the time in microseconds, we proceed to solve the problem of the distance, how far, which is making D the subject of formula from this equation as well. We have the velocity times the time. And that is given for the velocity of air at room temperature to be 342. So we are assuming that the speed of sound at room temperature is a constant that is given as 343 meters per second. So multiply that with the time given, which is the 8 seconds, and we'll have the distance to be 2.7 times 10 raised to the power 3 meters, or 2.7 kilometers, as the distance away from the lightning that struck. Okay, so that's how we arrived at our value for that. Okay, so we'll have some quiz questions as usual. To answer, I go through it. They're just a reminder of some of the basic concepts that I've learned in class about traveling wave, the units, and so on. Okay, so I appreciate a comment about this. And also, if you have questions, you can send me an email and we'll have every concern resolved as usual. All right, thank you. Have a great day.